In this talk, we will discuss a problem related to local connectedness of Bowditch boundary of relatively hyperbolic groups. My name is Ashani Dasgupta. This problem was part of my doctoral dissertation advised by Professor Chris Rushka at University of Wisconsin-Milwaukee. The problem stems out of a conjecture made by Bowditch as early as 1997. One may find a statement of it in his paper Tree-like Structures Arising from Continua and Convergence Groups toward the end of section 6. As we proceed through this talk, I will discuss more about this conjecture. But first, let me tell you a little bit about geometric group theory. The main theme of geometric group theory is this. We want to understand algebraic properties of a group G. To do that, we often use actions of the group G on some suitable topological space M. The topological properties of M then reveals certain important algebraic properties of the underlying group G. In this context, the notion of Gromov hyperbolicity is very important. We will discuss a little bit about it. It was introduced by Mikhail Gromov in his seminal paper Hyperbolic Groups in 1987. Let's understand what Gromov hyperbolicity is with a definition. Suppose KD is a geodesic metric space and ABC is a geodesic triangle in K with alpha, beta, gamma being three geodesic segments connecting A to B, B to C, and C to A respectively. Now for a real number r greater than 0, a point P is known as the R center of the triangle ABC if the distance of P from each of those geodesic segments is at most R. Now we are ready to talk about metric spaces which are Gromov hyperbolic. We say that a geodesic metric space KD is R hyperbolic if every triangle has a R center for a given R greater than or equal to 0. With this definition of Gromov hyperbolicity, we can now talk about hyperbolic groups. So a group G is called hyperbolic if it is finitely generated and its Cayley graph K with respect to any set of generators is Gromov hyperbolic. Here we are thinking about the Cayley graph K as a metric space. You can, for example, assign a length of 1 to each edge and so on, and turn the Cayley graph into a metric space. The relatively hyperbolic groups are generalizations of Gromov hyperbolic groups. I will not go into a detailed definition of it due to limitations in time. However, here is a set of motivating examples for relatively hyperbolic groups. They're the fundamental groups of complete non-compact hyperbolic manifolds of finite volume. These groups are heavily studied in geometric group theory. Now that we have classified certain large set of groups like hyperbolic groups and relatively hyperbolic groups and so on, let's talk about related topological spaces on which these groups act in a suitable manner. One candidate of such a topological space is the Gromov boundary. Now let's define it first. Suppose K is a proper hyperbolic space. A ray in K is a semi-infinite geodesic. Two rays are said to be parallel if the Hausdorff distance between them is finite. This is an equivalence relation, in fact, and we write del K for the set of equivalence classes. We say that del K is the Gromov boundary of the proper hyperbolic space K. With the notion of Gromov boundary comes the notion of Bowditch boundary for relatively hyperbolic groups. It's a candidate for a suitable space on which relatively hyperbolic groups may act and from which we can discover algebraic properties of relatively hyperbolic groups. Now, suppose G is any relatively hyperbolic group, then one often associates a Gromov hyperbolic space on which G acts in a precise manner. Due to time limitations, I am unable to describe the nature of this action. We say the Gromov boundary of that particular space X is the Bowditch boundary of this group G. And one may show that this Bowditch boundary is unique for a given relatively hyperbolic group. This was in fact shown by Bowditch. Now let's get back to the conjecture. In 1997 paper, Bowditch conjectured that if the Bowditch boundary is connected, then it is also locally connected. In fact, he proved this local connectedness with certain restrictions or tameness conditions on a special collection of subgroups of G called parabolic subgroups. He proved this for finitely generated relatively hyperbolic groups. In 2020, the proof in my doctoral dissertation, which was advised by Professor Chris Rushka, we removed the requirement of these additional tameness conditions and proved local connectedness of connected Bowditch boundary for all finitely generated relatively hyperbolic groups. Subsequently, we could generalize this result further and remove the requirement of finitely generatedness as well. Thank you for watching. I look forward to your comments.